Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is, well, this is the conclusion of the inverse Laplace transform. When I left you, you were working on these problems. You were to find the inverse transform each one of these. If you did it, I'm happy, and we'll look at what you did. But if not, you know what to do. Now let's see how you did. Well, the first problem is this one, and my clue is you always want to look at the denominator first. So we're looking at things in our table that look like this denominator. And the thing that we happen on is the sine AT and the cosine AT. Actually, we don't happen onto them, we happen onto this. S over S squared plus A squared and A over S squared plus A squared. So that's what this is looking at, and that's what I'm thinking about this being. And now I'm going to divide this denominator into each term in the numerator, breaking it into two terms. Now, this 6 will just sit here, and I have S over S squared plus 7. So you see, that lines up very well with what we have over here if I let A be the square root of 7. And so what's going to happen then is this is going to be the 6 times, and when I invert the Laplace transform, the inverse transform, I'm going to get cosine of square root of 7t. And this is, then this was minus 5 over s squared plus 7. And again, this matches up well, but the top does not match up well because the top would have to be the square root of 7 for it to match. But I will fix that because I will take the 5, I'll multiply 5 times the square root of 7, and I'll divide by the square root of 7. I'm multiplying by 1, I'm not changing anything. But that means the 5 over the square root of 7 can factor out, and then when I take the inverse transform, I get this. And that's the answer to this problem. Here's the next one. Now, when I start looking in my denominators, I don't find anything that looks like this in my table. But what I can do is I can complete the square on this, and let's complete the square. So when I complete the square, what I'm going to do is I'm going to say half of 8 is 4, and 4 squared is 16. So I'm going to add 16, but I'm also going to subtract 16 because I can't change the what's here, and then that's plus 21. So I added 0 in a clever way. Now this part right here, these first three terms, become s plus 4 whole squared plus 5. And that matches up nicely with this one and this one. So I've matched up my denominators, and now what I'm going to do is I'm going to work on the numerator to make the numerator try to match up with these. Okay, so here we have this, and 1 is not going to be, so let's look at this, and as we see, what we have in the numerator is s minus a, and we know a has to be 4 to match up with this. So we're going to add 4 here and subtract 4. We're adding 0 in a clever way. But now I'm going to distribute the minus 3. So this is 1 minus 3 times the s plus 4. You see I am making progress. And then minus a minus is a plus 12. And then this is going to be 1 and 12 is 13. So this is minus 3 times s plus 4 plus 13. And now I'm going to use the linearity. I'm going to take the minus 3 out in front. And I'm going to have this left, s plus 4 over this. But this, I know, is my cosine term like this. And so this is what I have that matching up with. And when I take the inverse transform, and s, that's going to be s minus a minus 4. So this is going to be e to the minus 4t cosine, and then it's going to be the square root of 5 t. So that's what we have there. Over here, what I need to have is I need to have the square root of 5 up there to match up with the denominator. So I'll put the square root of 5 there, but I'll divide by the square root of 5. Again, I'm multiplying by 1 in a clever way. So I have the square root of 5, and I will pull my 13 over the square root of 5 out as my multiplier. Then I will take the inverse transform of what's left, and I will have e to the minus 4t sine, and this is the square root of 5t. That is the answer to this problem. Let's look at the next one, and again, we don't have anything that looks like this, so we're going to complete the square, and we're going to start by factoring out the 2, and we're going to complete the square inside, and in fact, I'm just going to leave this 2 out here, and then I'm just completing the square there. So, 1/2 of minus 3 is, minus 3 over 2 squared is, plus 9 over 4. So I'm adding plus 9 over 4, but I have to subtract it because I can't change the numbers that are here. Minus 1. So this part right here, these three terms, becomes s minus 3/2 whole squared. And then when I combine these two terms, I get minus 13 over 4. So my denominator now matches up nicely with these from my table. Now notice that these are now hyperbolic trigonometric functions, but that's okay. So now I'll work on my numerator. Again, what I'm going to need here is I'm going to need an s minus a, and a is minus 3/2. So I'm going to subtract 3/2, and I'm going to add 3/2 inside the 3. And then I'm going to subtract the 2. Then I'm going to take 3 times s minus 3/2 plus, and then when I have let's see, I will have minus 3/2, and then 3 times this will give me 9 over 4, and then I subtract 2, and I will end up with a net of 5 over 2. It was 9 over 2, excuse me. I'll have a net of 5 over 2 left. And now I'm going to break it into two terms. The 1/2 sits there. Divide this into this expression. I have this. Divide this into this expression. Now, I'm close, but not exactly where I want to be, because I need to have a square root of 13 there. So I put a square root of 13 in and divide by the square root of 13. And again, I use the linearity. So this is going to be 1/2, then this is going to be 3. Then I invert the transform for what's left, and I will get the cosh of 3/2 t, cosh square root of 13 over 4 t, and then I'll go over to this one. I will pull out the constant, which is 5 square root of 13. I will take the inverse transform, and I will get e to the 3/2 t times the hyperbolic sign of the square root of 13 over 2 t. There is my solution. Now the next example is going to use partial fractions. So let's talk a little bit about that. We do long division until the degree of the numerator is strictly less than the degree of the denominator, then we use partial fractions. And for every factor in the denominator of the form ax plus b, we have a term in the partial fraction decomposition of a over ax plus b. And for every term of ax plus b whole to the k, we have k terms that looks like this. All these a sub i's are constants. And similarly, for each irreducible quadratic form, we have ax plus b over that. And if it's raised to the k factor, I have k of those terms. Yes, we're going to be doing this, and you probably want to review this a little bit. A quick way to do this, and I'm putting a note in your syllabus tab, but many of my engineers like using the Heaviside cover-up method, and this is a short MIT paper that talks about this. The cover-up method was introduced by Heaviside as a fast way to do decomposition to partial fractions. It's an essential step in using the Laplace transform to solve differential equations, and this was his motivation. So this paper is there for you to read, and I expect you to take advantage of it. Okay, let's look at this next problem then. This is what we have, but this time it factors. And so what we're going to have when this factors is we will get this. Now you see these factors make us realize that if I do a partial fraction decomposition of this, I will get a over s plus 2 plus b over that. And that makes me think of these things in my table because I have these factors of 1 over s minus a. And so what I'm going to do then is I'm going to solve this using partial fractions. And I will find out that a is minus 5 over 7 and b is 12 over 7. So capital H of s is this times this one plus this times this one. But then I invert the transform using this property, and this is my final answer. Now here are 3 more problems for you to do, and I'm going to encourage you to give these a go. You know what to do. Let's see how you did. All right, we have 3 factors here, so we have a, b, and c like that. And so we're going to use partial fraction decomposition on these. Now we're going to use partial fraction decomposition. You should review this, but this enables us to figure out with these 3 equations and 3 unknowns that a is minus 3, b is 2, and c is 5. That means g of s is this, but then I'm going to be using the same identity again for the inverse transform, and I'm going to say that g of s is equal to this. By the way, look, I divide top and bottom by 5 here to get this into the proper form. That has to be s minus a. I invert the transform and I get g of t is this. Now this one does have an irreducible quadratic form. That means it's a different partial fraction decomposition. And we end up here with 3 equations and 3 unknowns. When I solve them, I get these. And when I put those numbers in, I end up with this. Now here I have s minus 6, which is going to be nice because that can be inverted this way. But over here, what I have is not the right thing, but my denominator is s squared plus a squared. So I do some work on this. The first thing that I'm going to do is I'm going to break it up this way. But then I need to have a square root of 11 here, and so I multiply by square root of 11, but I divide by the square root of 11. So what I have then is I will pull out the constants. The 1 over 47 is out here, minus 28 in front. I invert the 1 over s minus 6, the minus. I get this. I do this. I have 28, and that is going to be the cosine. Down here is that one. And this is going to be minus, and this is 67 over square root of 11. Sine square root of 11, t. That's our final answer. Here's our last problem. Now on this one, what happens is we are going to do partial fractions again. Now here I have this as a over s plus b over s squared plus c over s cubed, and this is ds plus e over this. This is an irreducible quadratic form. That's why it has to be written that way. So I make my numerators equal using partial fractions, and I end up with 5 equations and 5 unknowns. They're easy to solve though in this case, and I get this is what a, b, c, d, and e are. You should verify all these calculations. So then I have this as my expression going forward. Now, when I invert this, I'm going to be able to use this first formula here to invert that. For s squared and s cubed, I can use this one. And for this last one, what I'm going to do is I'm going to break this into 2 pieces. I'm going to do it term by term. This is going to end up giving me a cosine term, and this is going to end up giving me a sine term after I complete the square. Okay, I guess I was skipping ahead too fast, but anyway, this is what g of s is. Here we complete the square. Up here we add 0 in a clever way and do the calculation and move things over. And now we have things that line up very well with all of these formulas that we're going to be inverting. So g of t is going to be equal to this. And you should verify those calculations. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.